As sir said, most of them also might be knowing. Before we would like to share some basic information. Sensors are basically like alarms, right? Wherever you want, what is happening, if there is any leakage, the sensors are being used. So this setup was bought nearly 8 to 9 years back. As sir said, what the father was working for LPG detection earlier, and CO2 was followed by another one. Now I work with hydrogen. So why we had to actually get this instrument and how we are making it progress even in this data, because world requires applications we are working on. So LPG gas detection was at that point of time, it was in a demand. That is why our senior scholar has worked on it. So what he has done is, he had already, there were many alarms, there were many sensors available which would detect LPG at a faster rate. But our motto was to actually make a nanomaterial such that it is a bit, what do you say, biocompatible. That is where we focused on the application. Even if you go outside, there are many good materials which can sense at a very low ppms at a very faster rate. At of even the cheap cost also you're getting. But innovation is something that we are focusing on it. There should be some improvement. So our colleague, I mean our senior scholar, had made nanomaterial with lactobacillus protein. He has taken curd, he has extracted lactobacillus bacteria out of it. He has actually added that protein content in the nanomaterial that he has prepared. So with the help of the protein content, he could see that there was an improvement in the response. That is how he has made a good innovation, how he is doing this period control. Next was CO2. CO2 or NO2 detection that was done by another man. What she has made an advancement was like, when she thought of doing something new, so she made almost for her 3 to 4 years, she has prepared nanorods, nano spheres, nano cylinders, nano sheets, some 4 to 5 different type of nanoparticles with different dimensions, and then she would observe the response. So that is where her innovation
The same material.
with the same material, everything same.
Structure will be
Structure will be different. So again, coming to the structure, the dimension varies. So what is the little bit improvement that we can do? That is where she is focused on. Coming to me, I have got, see, we have got the every setup and everything. So what can we do further? That is where even I have got, and I have done the literature on hydrogen sensing. So my focus of hydrogen sensors are already available in the market from since longer period of time. This is not a great innovation. They have been used for hydrogen gas leakage in aerospace, especially because hydrogen gas is a dangerous gas. So you need a faster alarm sensors which can detect these gases so that prevention of this blast will not, we need to prevent this heavy blast. That was being carried away from since longer time. Besides in abroad countries, these hydrogen sensors were also used for biomedical applications, which we were not aware of much, which we were not aware of much. Maybe certain institutes might have known about it, but not to a greater extent. So what are they? Certain things like lactose intolerance. If you know some kids and all, not only kids, even adults, they can't actually digest their milk properly. They have lactose intolerance. There are many people who are intolerant for many things. People who are intolerant for certain lactose and all, they can't actually digest their milk. So when this food or something like milk is being undigested, it gets settled over there. It has to come down because it is not being digested properly. It stays over there. So what happens? Because it is staying there for a long period of time, bacteria grows. This bacteria, after growing, gives up hydrogen. So from where does this hydrogen come out? It comes from your breathing. So a person who's functioning properly, who's tolerant, whose digestion is going well, there is no abundant growth of this bacteria and all, will normally exhale is hydrogen at a normal level between 1 to 20 ppm. But in case if it is exceeding more than 20 ppm, then we can basically say with this first basic test. This is not a accurate test, but basic test, we can say that with this sensor, if you are able to actually fabricate a material, and if you are able to actually let him breathe, so let him exhale his breathe on the sensor that we are able to prepare, it is biocompatible. From this, if your so-called breath is reacting with the material on the sensor, if it is more than 20 ppm, then we can say, okay, this person is suffering from this disease. Let us go for clinical diagnosis. Then we can go for clinical diagnosis. All these sensors are like basic preclinical tests. Before going to the clinic, you can actually get this sensors at your home only. You can basically test the portable, cheaply available portable tricks or devices. In case if you are like, okay, now definitely there is a rise in this hydrogen in my body, let me go to clinic, then we can go to doctor and go for clinical test where they will not use this breed. They use your blood, they use your so-called other serums or urine or whatever. That is like an advanced test. So these sensors are like basic tests for cheaply available portable sensors. So we have over here interdigitated electrodes. Okay. So our main motto was to these are electrodes. These are coated polycarbs actually. These are the interdigitated code electrodes which are already available in the market. Okay. These are interdigitated code electrodes. Material is actually coated on this. Screen printed of SPW. So these are all split printed electrodes on which actually the material is coated. Yeah, it is gold electrode. This down part is completely mirror. Okay, these are all gold electrodes. So what I have done is actually I have there are many materials that are already out. So what I want to do is like I want to actually get a biocompatible nanomaterial. Again, my innovation was also on to using biomaterial. Because it's taking towards those or toxic materials should not go because you try to inject certain things, right? So I wanted to prepare a nanomaterial so that it is biocompatible. For that, I have prepared copper oxide, I have prepared silver oxide, I have prepared nickel oxide, I have prepared zinc oxide. For all this, I have added chitosan, biocompatible chitosan. So these chitosans were added between ratios 1:2, 1:1, 1:0.5, 1:0.25, 1:0.125, 1:0.65. These are our materials. And for every set, we have prepared our materials. So what is the use of this? We just wanted to see for every material, for all this series of ratio, what is the response. So that on the whole, we can say for copper, this ratio was best. For silver, this ratio was best. For nickel oxide, this ratio was best. And for zinc oxide, this ratio was best. So that is how we planned it and we have synthesized. Coming to synthesis also, we made clear that it should be very, very simple. We have prepared silver oxide, nickel oxide, copper oxide, zinc oxide using only one simple method called probe precipitation come probe sodification technique. We have first done everything using probe precipitation, then we have made the ratios using probe sodification. The only difference that we made out was that for copper, for silver, for zinc, the precursors were acetates. For all these things, acetates, except for nickel oxide. For nickel oxide, we didn't get using nickel acetate. We have gone for nickel nitrate. Only for nickel, we have changed the precursor, but because we were not at all getting it. These are the basic synthesis steps. We have taken this precursor, and the reducing agent that we have used is sodium hydroxide. We have maintained 7 to 10 pH. Once we have got the nanomaterial, we have probe sodificated using chitosan. Using chitosan as our biomaterial.
Can you explain about the following the box application?
Probe sonication is not just, we'll show you the probe sonication. Probe itself is a rod. Sonication itself is a sound. So probe sonication, using this probe, certain ultrasound waves are being, they are liberated from the probe. So when you are actually putting a probe inside the solution, because of the high voltage sound, sonic waves or sound waves, these bulk nanoparticles are further fragmented, further fragmented into very tiny nanoparticles. That is the advantage of probe sonication. When you compare this digital, there's one more sonication out there, basic ultrasonic wave. Than this sonic waves produced over there, very highly, they're high volt, high strength, with high kilovolts they come out. So they break this nanoparticles into much more further. You will pakka get between 1 to 100 nanometer. 1 to 100 nano region. Usually what a nanometer is? Between 1 to 200 nanometer region are only considered as nanometers. So for sure using probe sonicator kind of a thing, because of their high strength, they will fragment, they will break these particles into much more smaller particles. So this is the benefit of probe sonication.
So after adding the silicon that component, you are taking that substrate and your props are getting it.
First, I'm preparing using chemical co-precipitation technique using these precursors called acetates and while sodium hydroxide as reducing agents. I'm preparing the material. Right? Now I take this material and I'm adding this sequence of ratios. If I'm taking 1 gram of copper oxide, I'm adding 2 grams of 5% and I'm prosonicating. That is one step. Then I'm taking 1 gram of copper oxide and I'm adding 1 gram of 5%. That is second step. Again 1 to 0.1, 1 to 0.25, 1 to 0.125, 1 to 0.0625. So this is completely one step. Now then I'll go for again, I've gone for silver oxide, I've gone for zinc oxide, I've gone for nickel oxide. So that is 4 steps were prepared.
Is there any other special reason why you choose acetate? Because there are so many forms, there are so many things like
Acetate itself, see among the precursors that we have like acidates, sulfates, nitrates and chlorides. Initially I've thought to actually do with all of them. I tried for copper with all of them. The rest and easy technique was acetate.
Anyway, now, acetates or nitrates will be dissolved in water.
It was very easy. That was first focus. Easily I got an answer to it. Rather than sulfates and nitrates and chlorides, that was a easy step. So that is why I made sure that for all the nanomaterials I use the same technique. Luckily it worked only for nickel acetate. For nickel it did not work with acetate. Then we are going for nickel nitrate. So this is the basic synthesis step that we have done, and finally we have prepared our nanomaterials. Now here comes the coating part. This is how we have coated. Coating you can do with various techniques called doctor grade method. You can simply use doctor grade method. Drop casting also. This is something similar to drop casting. Yeah.
dispersion solution.
We did not do any dispersion solution.
The nanomaterials, the broadcasting means nanomaterials is dispersion solution actually like ethanol, material,
You're talking about the solvents.
dispersion solution. Nanomaterials plus one solution only, you can do a broadcasting.
What is the same thing instead of a solution, we are using binding agent.
Now,
No, NLP. NLP.
ma'am, you're searching for anything.
I get. Oh. Yeah. So why we have to use NLP? Pure material can't be coated. We need to have a binding agent. Certain binding biological binding agents like aromatase, cellulose can also be added. But that was the next plan. First, we wanted to go with chemical binding agent so that it mixes perfectly. So we have 90% was the material, 10% was binding agent. This is like taking witness to the equation only. We have made sure that we can add 10% because if we are adding 10%, we made sure that even we are adding 10%. So 10% binding agent was added, 90% of material was mixed. And after mixing, normally we have coated. The general rod only we have coated. Yeah. Kind of doctor way, but we did not go for doctor way. It's kind of doctor way. This is how we have coated all these materials. Because these are electrodes, we don't go for any spin coating method. Because if you want any films, then you can go for spin coating. Then make sure that we are doing it in a normal way. Again, there will be a different specific topic for coating. This coating is like very much important, which can be analyzed by using air. Everybody are coated in the morning, but this much coating is not required. Make sure that this coating is very slightly the more slight and the more less layer, that is it. You need not put heavy amounts on it. It is just waste. When you give it to air, they clearly say it is not covered. So make sure if you are trying to prepare any sensors in the future, slight coating is more. And it will give you correct results, correct response also. So here comes the coating part. And after coating, I want everyone to start. This is a sensing chamber. Right now, actually, experiment is being done.
Can we have it in a batch so that no one can, yeah, can we have it in a batch? Like 5, 5, 6 members. Split the, 20 members are here, so maybe 10 or 8 people at a time, yeah, 10 members, not all at one go.
Let me be frank enough with you. First of all, it is is running, it is customer very good. And making sure that you should get good knowledge. So one can come and have a look. Even I am scared because it is very scary. That is why we made sure that even one or two members can have a look and go fast. If you want, you can have a photo and pass it. Yeah, I
Where the gas is passed.
will. You guys take a picture, I'll explain. That is why I don't want to open. That is what I don't want to say. Like, reduce done. Make it quick now. It is falling. Anyways, I've reduced it to 0. Now it is 0 only. If you've taken the picture, I'll explain. I'll explain all the components. Done? Sit. I just the vacuum also. So if you see your picture, you see there is an electrode, right? Electrode. On top of the electrode, there is a small pipe that is actually falling on the material. That is where the gas actually flows. The gas falls on the magnet. That is how it is. And at the end of the electrode, you see these connections. These connections are connected to the probes. Okay? Did you get the connection part now? The electrode is divided into 2 regions, right? Active region where the material is coated. If you see on your mobile phones, an inlet is exact, an outlet, you can say an outlet is exactly falling on this. Can you have a look at your mobile? From there, actually, gas falls on this material. And now the gas in the material is over here. Now, why is it reacting and how is it reacting? Because at the end part, you see two probes are being connected. Yes, these two probes are something. If we are supplying, that is, we are supplying voltage, right? We are supplying voltage to our probes. These two probes are going and getting connected to the below part of the electrode. Now, from this below part of the electrode, the power supply is then being connected to the active surface area. So at this active surface area, it makes sure it is activating the nanomaterial. So your nanomaterial gets activated. From the top, hydrogen gas is falling and there the reaction happens. There is no specific coefficient difference in the orders. There is only like two probes. Sorry, two probes and four probes. So these two probes are being connected. You don't the working electrode, counter electrode, difference electrode. You need it for cyclic voltammetry analysis. Here you will get to know the resistance values. More resistance. So now because you are supplying your voltage to these below part, this voltage is being carried on to the top part and on to the front part where you are coating your material. So what happens? The voltage that is being supplied is going, it is activating the material. Once your material is getting activated, it traps the hydrogen gas which is falling on it, it reacts. So out of this reaction, you will get change in resistance values. Okay, so this difference in change in resistance values only will give you which PDM is best, which PDM is not best. Okay. From very less voltage. Make sure you are using very less voltage. We are using 1 That is nothing but equivalent to your battery. Even if you are preparing any sensor, make sure you are also using a battery which is like very low voltage. So we have also made sure that we make it fixed to 1 voltage and we are using a 1 voltage. Now you have understood how to prepare the material being coated, how is the reaction happening, how to run the sample. So first thing, madam, what is that? So prior to all this, since you have prepared your own material, you just wanted to know how is it working. You just wanted to actually see how whether it is working, whether it is not working. Or not. For all this, you have to do the chemoresistive studies. Now, what are the studies called? First, we have fixed 1 voltage, but actually, what people would do is, will your battery be sufficient or not? You should know. So for that, actually, there will be a separate voltage studies. People will do from 5 voltage, 4 voltage, 3 voltage, 2 voltage, 1 voltage, 0.5 voltage also. From that, they'll make sure 1 voltage is giving a very good response. Then they'll fix that voltage. So we have fixed 1 voltage. Okay. You can all see there is 1 over here. Okay. Yeah. 1. So 1 voltage is being supplied to 2 probe. So that means the same is being supplied to the active surface area. Now, that is a voltage studies. Now, what is the main
different
purpose?
material, we have to optimize first.
Yeah, that is your bit, sir. Because we have made sure that one is working for us, we have fixed one. But if you want to study further more, not only for 1 to 5 voltage, less than that also, like some people doesn't even give any voltage, they'll do because their material is such that they doesn't require any voltage. If it's really like innovative, very chemically reactive material, so that voltage is not at all because we see certain things. They don't operate with battery now, sir. Temporary things. So for that you can actually do it. Next thing is after voltage studies. What is your main purpose? Your main purpose is to fabricate a sensor which will detect higher concentration or lower concentration. Very lower concentration. That is your main target, right? So for that you need to analyze. Like what we do is first we'll run between 1 to 50 ppm. Okay, if you are getting, that's good. Again, if you're getting, we'll be very happy. Then we'll be like, okay, if you are getting between 1 to 50 ppm, let us go for 1 to 10 ppm. Then we'll see between 1 to 10 ppm. From that, we'll fix. Advanced sensing setups will go less than 0. Point, very point detections are also being detected, which are like IITs and all. Okay. So for that, we'll actually do these studies. Something like this. You can all have a look. So like this, we'll prepare the sheets. Okay. So these are like, the first sheet will run between 1 to 50 ppm. In the second sheet, we'll run between 1 to 10 ppm. Then we'll get to know the resistance values using this formula. So this is the formula using which we calculate the difference in resistivity. Okay, this is how we get the difference in resistivity values for each and every ppm. We'll try to plot overall information. And we'll get to know between 1 to 10 and 15 to 50 ppm, which is the best ppm. The final ppm we'll select like this.
In countries, how can you tell that which PPMs are like you are getting better values?
Response, higher response. 7 is higher, no?
Highest peak.
The peak.
X-axis is PPM and what is index?
Yeah, x-axis is your ppm, intensity is your y-axis. Okay.
The response.
The rest. So let us all do one cycle now, okay? Since I've already fixed the material. So this is how we'll operate.
What is the formula you're using now?
I'll give you the formula. It is absolute resistance of analyte gas minus resistance of your synthetic air divided by resistance of your synthetic air into 100%.
So here we are taking synthetic and analyte as like a reference in, the test and control. Okay. Okay.
I'll answer your question.
Okay.
Okay. Now I'm starting one cycle for you guys. So this is our synthetic air. Yeah, another important thing is, now the synthetic air is connected to this MFC, hydrogen is connected to that MFC. Make sure that you are buying MFCs. MFCs actually vary for every gas. Synthetic air, it will be common, but micro flow controllers differ for each and every gas. So if you're working on hydrogen, buy that respective MFC. If you're working on some other gas, make sure you're buying that MFC only. So these micro flow controllers change with the density of the gases. Okay. First cycle. On the whole, you should make sure that you're maintaining everything to 100. Now I'm purely sending only synthetic air. I'm maintaining it to 100. No? Just have it. I'm running the sample. I've maintained 180 seconds. But if you want to cut down it to 90 or something, you can even do that. Okay? Sir, come forward. I think you were like very much. Yeah, you can come over. So now the data is being collected.
IoT based sensor,
I didn't get you.
IoT based sensor.
No, it's a plastic ceramic substrate.
No, Internet on things, like you're connecting it to the computer, right? So,
Yeah.
so it's like Internet on things.
No, it's not internet. There's no internet connection to that.
Okay,
No. See, I've run for 100, right? Next, I'm running synthetic air only for 85, and I'm sending 15 hydrogen. Then it will be on the whole 100. One cycle done. I'll turn on the vacuum. If I'll clean the environment, then once again I'll send 100. This time I'll send 80 and 20, making it to 100. Then I'll turn on the vacuum. So like this, I'll be doing till 50.
50.
Yeah, 50 till I reach 50.
Okay.
Okay. Then the similar thing is for 1 to 10 ppm. 199, 98 to 93.7 like that. Okay. So make sure you're maintaining to 100, adjusting both of them to 100. Okay. And the resistance values are captured by key 3. So this the speciality of key 3 is it can detect, can capture very low minute resistance values. Okay. So you can see the change in values over here. If it is stopped over here, you won't get any value over here.
It is like
In this, it's a 4-point drop. We are using only 2. Because 2 are enough. And if you see in the picture, there is a rod. What is that rod for? This one small rod touching the surface. See, I've told that voltage studies. After that, we are going for the speaking studies. See, people if they are unable to get, if they get between 1 to 50 ppm, they'll go for 1 to 10 ppm. If they are getting even 1 to 10 ppm, they'll be very happy. Say people are not getting from 1 to 10 ppm, 10 to 50 ppm, even from 50 to 100 ppm or 1 to 100 ppm also. The next option that is available for them is heating the substrate. So for that, you have a heater. So that, that is your...
This one.
Yes, this one. So that once again, with the help of this heat also, the energy will be supplied to the material. Again, your material gets activated. For that activation, you need this heating filament. So you can use that option if it is like really required. Okay. But generally make sure that innovation should be in a way that you need not go for high temperatures, high voltages. See, it's done. It's done, right?
Yes.
Going for the sheet one. Just replace it, right? Going for the next alphabet. Now this time, I'm going.
85.
Yeah. Yes, please.
you can use temperature if you want.
Yeah, present temperature set value you can. That is why furnace switch is this. That is why that rod is there. For that rod only this furnace switch. We have never ever used this another furnace. Hardly we have used only one for this. That could be for increasing much more temperature size. We have never ever gone for the next furnace. In this entire 8 years of our course, no one has touched the furnace. At the max, we have beyond the room temperature. That is not required now. Why? Yes, yes. That's true. Using helium, we can maintain that. Something like liquid nitrogen we can maintain. I think it's a room temperature. Never thought. I thought like a room temperature is fine. Why should we go for yes, yes. Yes. Yes.
That's pretty good.
Most of them.
But right now, I ask you for all this.
Plotting graphs, and we just take the data, we plot it in origin or expert high school.
Because most of the people instruments are with lab.
That doesn't all like we just got data back. We are just using the data and we're plotting it. Yeah, exactly. After this. No, cyclophotometry is not correct. How to calculate this? So once you get this data, use this formula. Okay, keyboard is not working. This is the formula. This is the formula. Absolute resistance of analyte gas, because we have passed for synthetic gas. So I'm telling resistance of analyte gas minus resistance of synthetic gas into 100 divided by once again analyte gas. That is how we get the resistivity. So this is how it is called chemoresistive gas sensing. Gas sensor. Now, if I talk, like I've already told you, if you need temperature, if you're not getting between these ppms, you have to use the temperature and you have to do this study. Luckily, if it doesn't, if you don't require any temperature, you're happy with this, you'll start plotting the graphs as I told you between x and y axis. After this, the reviewer definitely will question you, like they'll question, okay, you have done the studies, you got it. How long is your material stable for how many days? So make sure you're doing even the repeatability studies. for certain days, 30 days, 60 days, 90 days. So there will be a degradation after certain days. So once there is a reduction in the degradation or a saturation point has reached, once the plot is falling down, there you can say, okay, my material is activated or it can work till 60 days. It can work till 70 days. After 70 days, I've noticed that there is a difference in its response like that. So this is called the repeatability study. He'll even question you, fine, repeatability is everything is fine. What if it is put in an air where apart from hydrogen, some other gases are being leaked? Does it react only with hydrogen or will it react with all other gases also? So for that, you need to do interference studies. That means once you have got your ppm, if you have got to know at your 15 ppm, your hydrogen is doing good, till 60 days it is doing good with your repeatability studies. Make sure you're putting the same ppm, that is 15 hydrogen, 85 synthetic air. Run your hydrogen and keep running the same ppm with all the different gases. That means 85 should be your synthetic air, 15 ppm should be your isopropanol. Test is done with isopropanol. Again, 85 should be with your synthetic air, 15 should be with some acetone. Whatever we ask for. Usually people do this isopropanol, acetone, methanol, ethanol. These are all called interference studies. So that is how you will get interference studies. Say if you have satisfied him with showing 6 gases. Sir, I am able to actually give you the data using 6 interference studies, and out of the 6 interference studies, my material is doing good, then he'll say, okay, fine. So that is how you'll be able to give the data. You should even give the voltage data, but voltage data is not required. Since you are using only one voltage, you can say, you can satisfy the reviewer because these is everything is working at low voltage batteries only. You can say that. Then followed by your ppm. Temperature is not required, low temperature. Temperature is required, go for high temperatures. Then go for repeatability. Then go for interference. So this is how you will get the data. Finally, you will say your material is doing good. Okay. So for this repeatability, you need 60 days of data. So make sure you are running each and every day. You have to run each and every day. Then only you will get the data. This data, he'll definitely question because these days reviewers are like asking for the blind, the data, the raw data, and all. You have to make sure that you're providing the data. So even only with the help of data also, you will be able to actually support your evidence. If not, you can't support the evidence. This is one part. Here comes the mechanism part now. Why is hydrogen reacting? How is hydrogen reacting? So you have to be in a position to actually predict the mechanism between the prepared material and the reaction with the hydrogen. What is the main reason that it is being detected at 15 ppm? Fine, but how? Why? That is where the question arises. Then you should be able to clearly explain them, the reason behind it, the functional groups responsible, the chemical reaction that is happening, the temperature that you're providing, the electrons that you're making them activate, everything you have to detailedly explain. So that is where it is satisfied. Then your material is good, is doing good.
Usually, ma'am, the sensing mechanism is happening because of the high amount of electron releasing and all, right?
See, as far as the knowledge I have, there can't be only one reason behind this. This is all one thing. In order to even produce a proper mechanism also, you need to have a thorough characterization studies. See, if you have done, I've prepared copper oxide chitosan. The first question that he'll put is, prove me whether copper oxide chitosan is there or not. You have to do your XRD. He'll ask you, if I say that my band gap is very small, that is why the valence bond has reached the conductive bond, that is why it is reacting so good. He'll ask you to show UV band gap values. You have to do UV and band gap values. If I say that my material has got nanospheres at very prepared very nano level between 100 to 1 to 50 only, he'll ask you to show SEM. He'll ask you to even show TEM, correlate your STEM with your XRD, showing the Miller indices are correlating. there your Miller indices, if you are getting any HKL planes, you have to make sure that those are being correlated with your SID pattern, selective area electron dispersion. So say if you are even adding certain things, because in your synthesis part you will be left with nitrate acetates, they are not completely washed away. You will say, you'll say like certain groups are being responsible. So there are these groups, how are they coming? Then you should clearly show FTR graph. Say certain things are still there. Because of this help, the reaction is being enhanced. Or you can say the response was decreased because certain elements or certain substrates were still not washed away. So you have to show your FTR graph for that. So all the characterizations are like very, very important. One of the most important characterization for this is porosity, which is BET. Your BET gives you the pore volume. See, gases are something. What is a duster? It absorbs water. Similarly, gases, if they are to be absorbed, they should be porous nature. That means they are supposed to be hollow in nature. They have to absorb gases. There shouldn't be any solid. There shouldn't be any liquid. There should be lots of gas, empty pockets in it. So for this, you have to characterize BET. Show them you've got a very good porosity. If you are able to satisfy them, okay, because of all these characterizations, apart from that, they are even giving the porosity values. Because of the porous nature only, they are able to react and they are able to give this value. Then they will be satisfied. So BET is like very much required for this. And another important thing that we have come to know in our last 2 years, that we have for hydrogen sensing only we have implemented is coating of the material is important, but make sure the coating is not being removed easily. That means you have to prepare a material so that it is not hydrophobic. Sorry, it should be no, it shouldn't be hydrophilic. It should be hydrophobic. What even if it is washed away, even water is falling on that, the material should not be removed or it shouldn't come out.
So what are the binders? Usually they're using naphthalene binders, right? So what
Do much more research. Do research and find out that you're preparing a material such that it is properly sticky. And for this, what will you do? Which characterization technique will you use? Contact angle. Using contact angle, you'll be able to know, you'll be able to say whether it is hydrophobic or hydrophilic. If it is hydrophilic, it is waste. He'll say there is no use. Because no soon you add a water, your material is coming out. What is the purpose of that? Make sure you're preparing a very good hydrophobic material so that no matter even rain falls on it or anything falls on it, the sensor will have a very good duration period of time. 100 days, 1 year, 2 years, 3 years. Only with this study evidence report only, you can prove yourself. Then only you can file a patent, clear patent. So this is how all the characterization techniques, mechanism, everything is important. Literature is important, synthesis is important, coating is important, running the sample is important, thorough running of the sample, repeatable interval studies are important. After that, plotting them perfectly is important. Characterization studies are important, which will support your mechanisms, followed by conclusion part. So like this, once one cycle is done, I'll turn on the vacuum like this. Okay? No. It's already on. I made a connection also from using this stuff. So we are not using this tool at all. So for every one cycle, in order to make your chamber neat and clean, you turn on the vacuum, off the vacuum, then start the next cycle. Then I can go for the next cycle. So inlet is from these two, which are coming back and passing through this. So there you'll get the values. But 85-15 should get combined to forming it to 100, right? These both will mix over here and then come out of this, get into this, and through the small pipe that you have seen in your photograph, from there the actual concentration falls.
Why to focus on the sample itself? Why not in the definitely. What direction?
Because you wanted to actually study on your material only now, sir. How is it is reacting with your
The
material?
gas will not be connected to that.
And
Both are leaking gases. No, it will come in the same direction.
no, it will system as
The aim of one of the leakage, the gas, it will not directly come.
that is true. In real atmosphere, there won't be any special nostrils and all. For at least the basic studies only, we are doing so that whether it is reacting with hydrogen or not, how is it reacting and all, we are doing over here. Once it is doing good, then we can actually put it in the atmosphere. Obviously, no matter how far the leakage is happening, it can react only when it is coming close to it. It can't, it itself can't go and react till there. So it has to reach to this point, it has to reach. For that only, we are making sure that the inlet is falling on the sample. Analyte is your hydrogen, the ones that you are detecting. Synthetic is the general atmospheric temperature. Why do we use synthetic? Because even in your atmosphere, you will pure hydrogen come? No. Hydrogen will react with the surrounding atmosphere. Then it comes, right? Then it mixes and then it is falling. So for that mixing only, we are using 70% synthetic air and the next percentage of analyte, and we are mixing it over here.
But you said after fixing the analyte gas for 15, what is giving a drop to optimize that 15? How do you mixing the other interference? 15 ppm should be or
Actually,
everything will be.
no. We use a specific properties. Once the hydrogen is fixed, then we'll go for this. We are making sure that we are, if the hydrogen is for 15 ppm, we'll go for 15 ppm over here. We'll suck the respective gas and we'll make it fall over there. But the
Before
latest,
letting the synthetic gas and getting.
no, synthetic will be 85 only. We'll open this, we'll take the hydrogen, we'll make sure it is falling, and we'll run the gas. But advanced instruments are in such a way that they are not just one inlet. Some 10 to 15 inlets are being passed. Then I think there won't be a problem for that. You can use.
But it is too costly compared to SPC. SPC are carbon.
You can use anything can be used because it's been 8 years. These electrodes and everything are just we are using. Moreover, gold interdigitated electrodes are like they have this specific brand print that they will give good response. There is a very good conductivity. The main reason is for conductivity. So that is the reason why we are still using them. Actually, if you are able to coat your material on a directive FTO substrates, which are like highly conductive, you can just put that pins probe connection. You can yes, yes. I will. That is very simple. Normal thing only.
Is not vehicles and normal temperature. You have to use oven only. On oven right or air right?
No, I did not use any oven.
Air right only it's enough.
Yeah.
How much hours will it now?
Yeah, it will take some 3 to 4 hours. I did not put it in oven. I have maintained it at room temperature.
For real time,
How much time we can, if we are making the briefing, so how much time it will take to sense particular test? Because we don't need like that, so it will have some time, so how much time it will take to
That is why these sensors are fabricated in a way that they should quickly react. Quickly react means your nanomaterial should be in a way that it should give quick response. There are many sensors which will give result after 1 minute, 2 minutes, then it gives a test. It shouldn't be like that. More soon you actually exhale, it should give the value. That means your material, the prepared material should be so good.
But what about your material?
These, the material that I have prepared, we have gone for characterization studies. We can predict the mechanism, that we can even correlate the mechanism with the characterization studies. But in real time, we did not actually quote it and we did not actually sense it. Real time, we did not do. That is our like future plan. Real time, if we do, then we can say. That would be a kind of patentable. Sorry? Real time
But
monitor.
we will have real-time analysis also, ma'am, in terms of sensor.
They will ask, they will ask, they will ask. For the real-time analysis, we need to have portable device.
Portable device.
In the device, if the real-time analysis machines or any device are there, what can we do? We can simply quote the same material and we can check. That's it. That we did not do.
One more question. What about isopropanol interfering agents?
Interference gases.
Because if it's metal means, how can you make it in metal?
Using this microscope. Once you have come to know your hydrogen concentration, if you're maintaining it for 15 ppm, similarly, you'll take the isopropanol gas, use this microscope over there, I mean, tipper, you take 15 ppm, how much ever you doing? Whatever it is, everything is digits only, we'll take 15 people, we'll make it follow the sample. Directly we'll make it. This is for,
Yes, I thought that you will make it in the
no. Actually for that, you need to have different gases set up. Only two cylinders are connected to this. If we have many micro MFCs, many cylinders, these advanced setups are already there. Sometimes like in IITs and foreign countries there are there. Right now we don't have that. In that case, you can send all the gases together and you can measure. Yes, even if two more connections are there also, we can send.
Material mg for protein test. Mg per ml or mg per
Very less. Actually, in my paper I have written, it is actually equivalent to the surface area.
surface area.
Yes, surface area.
How many mm on that surface area for gold SPW? That surface area.
I think it is some. I tell you the surface
I
area.
think it is same for all the screen printed
A surface area is common for all the screen printed ones.
Okay, so
There won't be any.
So you also calculate the active surface area. Using random sensitivity, like critical sensor, we are calculating the random sensitivity. Using random sensitivity equation, we are calculating the surface area. For this, it is required or
Maybe. Seems interesting because I did not do the calculation. What I could say in my paper is calculated the surface area and I have given that calculation.
how much active is your surface area? How much,
See how much active means, it is very clear. The coating that you are coating is itself is an active area, right? If you get the surface area, that itself is your active
surface area.
That's it.
They are asking to put in the calculation, they are asking
For that, a mathematical calculation is required. I
maybe
guess.
it is quite for chemical sensor also. For this, they might
Yeah. For the next batch, I will give. One final thing I want to say for this class. Where are those once you have done everything, latest electrodes are these flexible I will. You stand in your place for the next time, stand in front. I will. Anyways, tell one more time. Typing by 40 minutes. అది కాదు డిజిటల్ ప్రొటెక్షన్ అడుగుతారేమో
జీతా అంటే మన దగ్గర